Hey, what's going on, folks? It's Mike here, and welcome back to my D programming language series. In today's episode, we're going to be taking a look at the DMD compiler and how to just understand what it's doing to our code, the transformations, the generated assembly. We want to go ahead and take a look at that. So let's go ahead and see how to do this with the DMD compiler here. And of course, you can do these things with LDC or GDC, the LLVM and GCC front ends as well with the D language, but I'm just going to show you a DMD for now. Now, before I go ahead and begin here, many of you, if you're coming from C++ or other languages, you're probably familiar with Compiler Explorer. So this is godbolt.org, really, cool last name for Matthew Godbolt, and of course, Compiler Explorer here. Now, what's cool about this tool is you can see on the left side some code here, and this is, of course, in D that I have selected here. I'll talk a little bit more about that. And then the right side is the generated assembly code. So, of course, you can just hover over some of the lines on the left side, and it'll usually correspond to something on the right side. So you can see the colors or just where the screen is flashing to otherwise get an indication of where things are. In this little experiment, I just have some different ways to assign something to 0 just to show off, I don't know, some different strategies of, well, how would I use this? Why is it useful to be able to read this assembly? So clearly you can see which strategy here results in the fewest amount of instructions, and that's a way to optimize your code and sort of understand what's going on. Now, that's kind of why we care about what happens, because, well, eventually what happens with our D code is it does get compiled into assembly. It's compiled language, and this gives us sort of a way to run code or our binaries on a machine really, really, really fast. Now, there's a little bit more going on here, which I will talk about later. You'll have to subscribe in this series. I want to talk about betterC, which is a really cool feature of the D language that removes some of the runtime and makes your code even more portable, I'll say. You know, in short, that's one of the motivations for betterC, to strip away the D language runtime, replace it with your own, or again, have less sort of overhead with if you don't need some of the features in the full D programming language. So anyway, stick around for betterC. We'll talk about that later on in this series. But what I want to talk about, though, is how do I get this assembly output out of the compiler? Because maybe you don't have access to Compiler Explorer, or maybe Compiler Explorer is not updated to the latest version, or whatever reason, you just want to know how to do this. So let's go to the D language website here, dlang.org. I'm going to go to the documentation and the command line reference here. And I'm going to go ahead and just search for assembly or assembler, and we'll see it's this flag here, VASM here. Now, of course, you can find these flags here by doing DMD help. And usually if you just grep through the help here, let's just try grepping through and finding assembler. Let's see if we're able to find it there. For some reason, the pipe's not working. Maybe if I put in the exact flag here, let's see if it finds it. Nope. Oh, let me try one more time. There we go. It's just something like this here. There we go. You can only search for the flags here. I don't know why that wasn't working. Maybe with just dash H does a trick here. Dash H, excuse me. But anyways, let's go ahead and try this flag here, VASM, with this code. Now, to make it just a little bit more interesting, we should add some functions here. So I'm going to add void func1. And I don't know, we could do int x equals 72. Maybe in our main function, just give an instruction y equals 42. Something like that here. And let's go ahead and just run dmd-vasm, pass in our file here. I'll run it, and it's just going to dump out the assembly just like that here. So we can see here we've got function 1. There it is, function 1. And then in our main, we've got the D main function here. Now, already what's kind of interesting is this gives us a few different insights. One, you might notice that the names are sort of mangled here. That's just, one of the features here. And you can see that this, by default, the file name matches the module here. Let's see if we give this a different module name here. Let's just call it module Mike, for instance. And let's go ahead and redo this. And of course, you'll see that the module name is first, some symbols here, and then func1 here. And we can take this a step further, for instance, if we make this particular function extern C. So for those of you who want to talk to C libraries easily, and we run it, now you'll see that this name's not mangled anymore, and you can just see func1, the label here. Okay, so this is one way to kind of view your code and understand what's going on by dumping out the assembly, playing with some of the D features that you need. But again, I found this really, really nice, especially if you're working with D and trying to work with other languages just to see what's going on here. Okay, so anyways, that is part of the idea here. Of why it's important to understand this assembly. Of course, with this example here, as I showed in Compiler Explorer, you just want to see which strategy of algorithms or techniques that you're trying actually reduces or maybe calls the right assembly instructions that make things less expensive. So again, just really, really cool that you can dump out the assembly. And ultimately, the assembly code, for those not familiar, is the machine, the basically text representation of the machine instructions. Okay, so this is what we understand, and then the computer is going to generate the opcodes or operations with the effective arguments for us as we know. So anyways, that's really, really handy here. So, and that also helps us just understand, again, what our compiler is doing. But the other flag that I want to show you, I didn't find it in the documentation manual, but if you search around here, so I'm going to make my window a little bit bigger here just so we can see what's going on here, which is pretty cool here. And I think, let's try to grep for it again here. I believe it is VCG. I don't think I'm going to find it here. Nope, didn't find it. That's not what I'm looking for. It's not documented, although it might be, or maybe it'll come in our release here. But the basic feature that you can do is -VCG-AST. And since it's not documented, I don't know if this is a call tree or a call graph, but the abstract syntax tree. And again, this is the same thing we saw. Let me go ahead and open this up here again in the community page here. And I've showed this in a few previous episodes here. So if I go to resource, actually run.dlang.io, right, we have the ASM for assembly option here, but we also have the abstract syntax tree after all of the semantic phases here. Okay, so what does that mean here? Well, let's just do an example with what we got. Let's go ahead and do the same thing with main.d. And nothing is dumped out here as far as the terminal goes, but if I do ls, I'll see I get this file here, main.d.cg here. Let's go ahead and just open this one up here. And if I open this up, well, I can see some things that we've written here, like module mic here. I see we've got this import object, and this has to do with some of the language runtime here. I've got this extern-c function here, func1 here. I've got main here, and I've got some other things here. So the DC main here, and if I scroll down, I've got a whole bunch of other things here, okay? And this is basically where our program starts here, okay? So why is this sort of interesting for us to look at? You know, is this just a more confusing version of the code on the left side? No, but this is what we'd say our code lowers to or gets transformed when we use certain abstractions in the D language here. And this is what compiler writers do to basically give us, you know, very powerful abstractions so we can write D code, and then we transform it into maybe a simpler form. And then this form here that I'm showing right above me gets transformed into the assembly code that we saw previously. So let's just do a little bit of an example here. For instance, let's get rid of some of this. In fact, what might be interesting to do actually, just to show one more flag that I haven't shown. And let's see if I can search for it too. Optimize, let's see if it finds it. Yes, -O here. Okay, so I can see how to find that here. Let's try to optimize our code. Let's see if it gets rid of anything here. And let's see our vim main.d.cg. Let's see. In this example, I guess it's not really doing anything. So yeah, it's not going to really get rid of anything. But that's the optimization flag here. Let's see if I run that with VASM. And yeah, it's just returning our function here. Actually, we can see the compiler was smart enough anyways just to get rid of, right? It doesn't really do anything. There's no assignment here. So I guess we got some of those optimizations for free. In fact, I wonder if I get rid of extern C. Let's see, we'll just delete that whole function. No, it'll keep it here. Right, I guess we might need it or to call into it or something. But so anyways, it's kind of interesting. We get these optimizations that can also change some of our assembly code here. But the thing that I want to show you, just to make this a little bit more interesting, let's get rid of that function here. I was going to see if the optimizer could do it. Is to use, let's just use, you know, something that we're relatively familiar with, like creating an array here. I'm going to use auto here. I'm doing that on purpose here, just because I want to see, well, what's the compiler going to generate for us, right? And to know for sure, I like to use VCG-AST here. So I'll go ahead and compile that code. Let's go ahead and look at main.d.cg file. And we can see that auto becomes in array, right? A dynamic array here of integers. So that's the type that's inferred by default. So if you're wondering, is it going to be a long? Is this going to be a short value? Is it going to be a char? Or, anything that could fit the numbers 1, 2, and 3. Well, int is the, deduced type here, okay? Which is totally reasonable and probably the right thing to do here. So let's look at some more examples here. Let's do a for loop for int I equals 0, I less than, 3, I plus plus. And I don't know, let's access the array at I and equal to 5, something like that. Okay, let's go ahead and see what that gets lowered to. So I got to rebuild. Relook at it in Vim, and then we see here, well, if you've ever wondered how this feature where I can sort of initialize my value I within this for loop, but it's scoped to only the for loop, well, it sort of makes sense that a new scope is created here. So you can see that with the curly braces, but the compiler is doing the hard work for you, right? So you don't have to write your code like this, okay? So again, that's kind of the insights here. And then we leave that initialization empty here. I have I less than 3, I plus plus. And then we're setting our array value. Now you can see array indices take in what would be a size t or a ulong, so we get that cast here for free. Again, we can upcast it, no problem there. So again, the compiler takes care of it. Okay, so just nice things to see here. Let's see another abstraction here. So if I use for each, for instance, let's do for each element in our array. Let's try to do the same thing here where I set the array element to 5. Okay, so we could go ahead and recompile this and see what's going on here. Well, this time, again, looking at this second block, which corresponds to lines 10, 11, and 12. Again, I'm creating a new scope basically every time I'm doing this for each loop. And let's see what's going on here. The compiler is, again, basically making a copy of this array here. Right, it's saying underscore underscore R2 equals array here, which is up here. That's the thing we want to reference. And then it basically transforms a for each loop into, well, a for loop, right? So again, this is the compiler working for us so that we can write things nice and easy for each element in an array, right? We understand that. But at the end of the day, it's still some for loop, and then that for loop will get translated into assembly. So again, just how these things work here. And then you can see that we create an element here. That's int element here. We set it to whatever the value is, or rather the index. That's sort of the key here that we're incrementing every time here by one unsigned long value. And then we set it to 5 here. Okay, so kind of interesting here. Let's do this one more time here. Let's go ahead and take a look at for each. I'm going to use ref this time, which I believe we have talked about or seen. Let's go ahead and recompile that. Let's go ahead and take a look here. Let's go ahead and see, is there a difference? Well, already I can see this one's got scope. This one's just got int here. So again, the compiler is doing something just a little bit different for us here. Where again, scope is to, if you're not familiar with it, one, you're learning new features by using this tool here, but scope is going to help us not have this sort of value escape where we're sort of temporarily setting things. But if we look at this, it'll look pretty similar. We've got some keys. Again, it's a for each loop here. But this time you'll notice ref int lm for element here. And, well, what is using a reference type here, making this a reference type here do? Well, it'll actually assign our array to 5 here, right? So again, that's a little bit of a difference here. Let's go ahead and use write line here and write out our array just to remind folks, if you weren't familiar with this, what's going to be the difference with when we run this code. And let's go ahead and import the write line library. Let's go ahead and actually, we'll just build this again here. And run it. And oops, I guess I should, because I've done it in this for loop as well here. Let's set this one to 3, this one to 4, and this one to 5. And let's go ahead and just write out our array after each time here. And go ahead and quiz yourself again if you're just not familiar with this ref keyword here, what's going on here. So let's go ahead and compile it and run it. And again, this is going to be 3s, no problem. This is, again, not going to modify the value. We're just accessing it for reads. So it doesn't really matter how we mutate the value within that scope. But this one, of course, is going to modify that value. Okay, so I hope that makes a little bit of a sense so you can see how things work. If you are curious, I believe it is going to be a change in the language as well soon. Let me go ahead and Let's just open up this main.d.cg file. I believe in the language in the future, you are going to be actually able to make reference variables too. I think that's a new thing that's coming. Maybe I just haven't updated my compiler at this point here. But anyway, sometimes you just learn some little like tricks or things and you're like, oh yeah, I can use scope or a new keyword. But it is really useful. And where I do find this stuff super useful too is if you use a template. Let me go ahead and just use one more example here really quick. Let's just create a new data type here. I'm just going to call it type T, and we'll just use T and then, some value here. And then if, for instance, I create this type here, let's just use auto here, T equals type, and let's use, I don't know, float, something that we haven't used here. And then I said T dot value equals 3.14, something like that. Let's make sure that it compiles. Let's see, what did I do? Probably forgot when I was constructing this. Let's see, something like that. There we go. You got to put your parentheses here because this is the constructing the struct. But let's see what I actually did behind the scenes here by just looking at CG here. So of course we can see our struct here, so no problem here. And we can see here that when I set up my float here, remember what happens with a struct is all the values, since it's a value type, right? T here has some .init initialized property or init here. And since it's a float, which we instantiate as, that means I get not a number for a float here for that particular type here. This is just the assignment here. No problem, nothing strange here. Let's see if we can actually find the struct type. Maybe if we scroll around here, we can find it. There we go here. Type. And this is the templated version here for a float. Here's the struct type, and then here is the instantiation. Let's just go ahead and highlight this. Line 64 to 71. Oops, you can't read it if I highlight it, but we can do something like this here just to highlight most of this block. Well, you can see again, I've got the struct type with float substituted in for value, right? So that code has to be generated somewhere for our type float. Basically that's how it works. And you can kind of get insights as to what your expansions are. When we looked at mix-ins on this series, we also did see the mix-in keyword. Let's see if my grep is working here. Grep mix-in. Let's see here. Oops. DMD help dash IRN. I can see it in this code here. Let me just do DMD help here. Dash help. That's what it is. But that's another way to kind of see what's going on here. But of course, your mix-ins, actually, let's just show it. Sorry, one more thing here. Just got to show you all the stuff that's going on here. Let's just use mix-in, and I'm going to do I equals 7, something like that, right? A mix-in is just a string of code here. But let's again see what's going on in the compiler, right? Our compiler's got to know about everything before we translate into assembly code. And of course, this is a mix-in, so let's give it a type. There we go. I is shadowing. Oh, I used I twice. I was trying to pick something. It doesn't really matter. JI. Okay, that's fine. But let's go ahead and look at the main.d.cg file. And again, you can see that that code is also mixed in. So, right, you can use the mix-in flag directly, or you can just use this, and it's going to dump out basically everything before this gets translated into assembly code. So there you have it, folks. In this lesson, hopefully you understood a little bit more about some of the cool stuff that we've got here. The VCG-AST flag for the DMD compiler, or of course, you can do VASM here. And it'll dump out all the assembly code. So as soon as I start, importing some of these libraries, I really mean you're getting all the assembly code. So that's kind of cool here. And that's actually one of the reasons why sometimes I use betterC if I'm just exploring with like operations, because it gets rid of some of the runtime, so I can explore things better. But anyways, those are a few different tips here if you want to get into the sort of inner workings of the D programming language. Anyways, as always, if you enjoyed this, you can track your progress on course.msha.io for the D language series. Same videos you're watching here in a distraction-free environment. And let me know what you folks think. Hopefully that was interesting for you to learn a little bit more about D, some of the compiler internals, or how to get some of the information out of the compiler and see how your code's lowered and transformed into different forms. Again, I just think it's super useful, and it's kind of fun just to see the little tricks that enable different programming language features. So if you're into compilers or programming languages, find out, if you're using D, LDC, GDC, how to get this information out, and it might just help you understand a little bit more about the programming world that you're in. Anyways, folks, thanks for your time and attention, and I'll look forward to seeing you in the next one.